Hello, good morning, everyone. How's it going?
Hi, Professor. Good, and you?
Good, thank you. All right, so we were talking about a couple of questions in our last class for conservation of energy. In particular, we were looking at when you do have energy transfers, energy inputs or outputs, how do you calculate it? And we have done two problems, right? One's involve simply the gravitational potential energy or work done by gravity, depending on if you want to include Earth in your system or not. We have also looked at one problem. You either have the elastic potential energy stored inside the spring, or you have the work done by the spring, depending on if you include spring in your system or not. There's another type of problem that involves friction, the work done by kinetic friction. I had one of the examples that I posted along with last Monday's, with our Monday's lecture notes. So you can check up that question there, but I wanted to use another problem to go through an example where there's friction. This one is one of your homework questions for this week. Okay, so let's take a look at this together. Maybe you have already done this, or maybe not. We have a small block, and this block has a mass m. Now, noticing everything here is kept as a variable. So that's something we need to be comfortable with. Get comfortable with there's no numbers, just a variable, but m considered a known quantity, okay? Now, if it does have numbers, and then you can plug in at the end, but the physics is the same. So it slides up with a velocity v, initially is on the frictionless surface, but then once it starts up the ramp, it has a rough surface. It tells us the coefficient of kinetic friction of the box and the ramp is mu. Okay, it's asking when the block has a velocity kv. Now you might notice thinking this is a weird way to tell you the velocity, but simply tell you what the velocity is. K is a fractions between 0 and 1. So if K is 1/2, right? So this is really, okay, when its speed is half of the speed that it was before, then what is a height h? So simply, now this fraction is represented by K, okay? So what is a height when the speed is kv? So we're going to use conservation of energy to solve this. So how do we solve a physics problem? The first step is always to draw a picture. Now in this case, the picture is already given. We read the problem, we interpret what it means according to the picture. And we should think about the physics we're going to use. And I said, well, we're using energy approach. And we have to choose our system and the initial and final point, okay? All right, so let's solve this together. What system do you want to choose? Anybody would like to give us a choice?
I think it would be maybe a little easier if we included the Earth and the box.
Okay, so since it's asking about the block, well, it makes sense. We include the block, of course, and it does have a change in height. So if we include the Earth, we can talk about the potential energy rather than doing the work done by gravity. That's oftentimes is simpler, and yes. Okay, all right, so what about the rest of you? Are you happy with this choice of our system?
Easier.
Okay, all right. So let's define our initial and our final point. Where do you want to define to be the initial point?
Probably at the bottom where it says initial position.
Okay, it has told you where the initial position is or initial moment. This would be our initial moment. And notice that whether it's this point or when it's like right at the bottom of the ramp, it doesn't make any difference because it is frictionless. It's going to have the same velocity v, no matter which one of these points you look at, okay? So when it's really close to the ramp or a little bit before the ramp actually doesn't matter. So we're just gonna choose what the picture give us as a initial moment. Finally, which would be our final moment, the picture indicated, well, there's a final position that we're interested in. At this final moment, the box is at a particular height h, and we want to find what h is, okay? And the box also has a speed is kv. It's not completely stopped yet, okay? We're not reaching the highest point. We're just reaching the point where the speed is k times v. So that's what we're trying to do. Okay, so that being said, let's try to label and figure out all these quantities. E final and E initial. So why don't we start with the initial energy of the system? So initially, when the block is right here, what is the energy of the system? What kind of energy the system has?
Maybe kinetic energy.
Kinetic only, very good, 1/2 mv squared. And since it's at the bottom, if we set the reference point to be the lowest point, so it has no potential energy, okay? So it's the lowest point. And at this final moment right here, what kind of energy the object, the system has?
Potential energy.
Potential, very good. And that is mgh. Anything else?
I think it also has kinetic energy because K is between 0 and 1, and it's not, so we know it can't be 0, so it has to have some kinetic energy.
Yes, it is still moving, very good. So we do still have kinetic energy. So both of these will be included. Excellent. And there is no energy input because there's no other external forces that is making the box go faster. And what about energy output?
I think there isn't any because we chose Earth and the block, but if there is, it's friction.
There is friction. So the friction is opposing the direction of motion and it's slowing the object down. It doesn't definitely is taking energy out of the system because it's slowing it down. So the energy output in this case will be the amount of work done by friction. And it's the absolute value of that work. We're just taking the magnitude of that work because the work done by friction is actually negative. So everything, you can see this is straightforward, except we just need to work out this term. So let's do that, okay? So work done by friction, by the definition of work is, what is the definition of work? Let's remind ourselves, is force dot into displacement. In this case, my force is, let me draw my force. Force is down the ramp, okay? And your displacement is up the ramp for an entire length of the ramp, delta x. These two forces, the two vectors are opposing each other, they're in different directions. Okay, so I calculate this will be frictional force dot into displacement, and frictional force and displacement in opposite directions. So it's negative, the magnitude of the frictional force times the magnitude of my displacement. So delta x represent the entire length of the ramp, how long the ramp is. Okay, so that is labeled already for us. All right, and what is my friction? Friction is the kinetic friction coefficient times normal force. Do you still remember that? It's mu times n times delta x. And again, what is my mu? What is my n? My n, the normal force of an object on the ramp. I expect at this point, you can say what the normal force is right away. What is the normal force?
So it's mg sine theta.
Yes, it's one of those, right? It's the component of gravity, but it's the cosine theta. It's the cosine. So just if you are not sure, when we are not sure, simply draw a little diagram to help us remember. This is theta. So it's mg cosine theta. All right, very good. So mg cosine theta and delta x. I'm still keeping delta x the way it is. However, if you look at this, the given quantities are m and v and theta and mu. H is unknown. What we are trying to solve. Delta x is also an unknown. We don't really know what delta x is. So if you want to solve for h, you want to leave h to be the only unknown variable in there. Everything else is a known variable. But then we got a delta x, so we need to get rid of delta x. And then luckily, look at this triangle of the ramp. Delta x and h, they are related, right? So if you look at sine of theta, sine theta is h over delta x. The opposite side over hypotenuse, which means my delta x is h divided by sine theta. So I can replace my delta x by h over sine theta. Okay, and then this becomes cotangent theta. So mu mg h over cotangent theta. Okay, and this is the only unknown variable there is. So the rest of that is math. So if you now plugging everything into the equation. So I have written this out already. E final minus initial equals E in and E out. Plug in these energy terms that you just calculated and you will be able to get the final result. I'm not going through the algebra steps, but this is something you could try to work out again by yourself. Okay, so this is an example of how you do when you have friction. Simply consider the work done by friction as the energy output. Okay. All right, any questions about this problem, about this homework problem? All right, okay, so we are actually going to move on now to a different topic. We are looking at momentum. So we talked about energy, now let's talk about momentum. You probably, you have already done a momentum lab, right? So you have already seen some of these concepts. Before we talk about momentum, there is another concept we need to put in there because later on we will refer to the center of the mass concept when we do momentum conservation. So center of the mass is fairly easy to understand. In fact, I will post a video regarding a high jump, Olympic high jump, that there's a person who invented Fosbury, who invented a different way to do high jump. So instead of making your leg lifted over, is flipping backwards. So the back of his body, so he's using his back of the body facing the pole, and then he's able to jump much higher. The reason for that is when you're doing this backflip, your center of the mass is actually a little bit lower. So you don't have to raise your center of the mass to be as high as if your legs are up. Then you have to raise your entire center of mass to be much higher. So this is the invention of a different way to do the high jump, and he won the gold medal for doing this. And it's related to the center of the mass concept in physics. The center of the mass is very simply easy to understand, is the average position of the mass. You have all the mass, and what is the middle? What is the average position, right? So if I have a very homogeneous pen, like the pen is made of the same material, it's of the equal thickness everywhere, then if I want to find the center of the mass of the pen, I just need to kind of find a place to balance it, right? I need to find the middle point where I can balance this pen. If it's homogeneous, usually it's simply at the geometric center that I could balance it. It's not quite exactly homogeneous. It is a little bit heavier, so I'm a little bit shifted to my left-hand side. So this is how I will balance an object by finding the center of the mass. And you have already done this question online. So if you're trying to find the center of the mass of a donut, where would you think the center of the mass is? Where would be the average position, sort of the middle of the donut material?
In the center of the hole.
It will be the center. Very good, because that is the average position of all the masses. Very good. And it is okay. And you might wonder, there's nothing in the hole, and that's okay. The center of the mass can be outside of your body, can be outside of your material. Okay, so that is possible. To calculate the center of the mass, the coordinates of the center of the mass, we have some equations to use. For you, if you have a lot of different particles or different points, where we talk about the particle model, is if you can look at this object and it's the shape and the size of it doesn't matter as much. You can view this as if it's a point. It's a point model. If you have a bunch of those different points, how do you find the average position of the masses? Is, well, each of the mass has a different position. Mass 1 has a position 1, right? And mass 2 has another position 2. Mass 3 have another position 3, and so on and so on. And they all add up, and then you divided them by the total mass of your entire collection of the little masses. So this is simply from the definition of the average position of the masses. You can see I'm doing an average position of the masses. So this equation simply represents the average position of the masses. Okay, now if you have a continuous distribution, like these little bits, they're not discrete, they're all connected, right? Our object in daily lives, we're all looking at a continuous distribution. Then you have to change them, the sum, into an integral. And little bit of mass is little dm. You integrate all the masses. We will look at examples for both of these, okay, later on. Now, if you have a combination of the two of them, let's say each of the object is a continuous distribution, but you have multiple of those objects, and then you will simply find the center of the mass of each of them and treat them as a collection of little points. So they have two different points, right? Each of them has a center of mass, and two together are 2 points connected. So it's sort of a combination of these two methods. But we will explore the mass aspect of it slowly, one by one. Okay, so that's what we just talked about. How do you find the center of the mass of an object? So position is R of the center mass of the object, is to add up all the positions for different masses and divide it by the total mass. Okay, so if you want to look at the X and Y component, now recall the X component is just the average position of the X coordinates, the y component is just the average of the y coordinates, because here we said this is R1, right? R1 has x component, y component, and it could also have a z component. So you can calculate each of the components separately. Okay, so let's look at one example, how we do this, all right? Here is one example, how to calculate the center of the mass. I have a triangle, and this triangle is made of three different masses, one here, one here, one here. A collection of 3 points. The rod in between, that's very light, and we don't consider that has anything. So it's really just where we have these points. So now I want to find the center of mass of this triangle. I need to find, okay, they're all in the same plane. I don't need to worry about my z direction. I just need to worry about the x and y. So what is the average position of the x and what is average position of the y? Use our definition. You can see that the average position of the x is mass 1 times the x position of 1, and mass 2, x position of the 2, and mass 3, x position of the 3. So I'm gonna call this your mass 1, mass 2, and mass 3. What is the x position of mass 1 right here? It's at x equals 0, y equals 0, right? It's at 0, 0. So you can plug in 0 for the x position. And my second mass is also 1 kilograms. And what is the position of my second mass? It's at x equals 1 and y equals 0, 1, 0, right? So I'm plugging 1 meter for the x position of my mass 2. The third mass is the 3 kilogram mass. So I do 3 kilos times the position of the 3. Where is the position of the 3? It's exactly in the middle, right? It's halfway between these two. Because this is a triangle of 60 degrees, they're all equal. So this is exactly in the middle, okay? Because this will be 30 degrees. This will be 30 degrees right here. And this will be exactly 1/2. Okay, so that's 0.5 meters. That's the position of your third mass. So average it together, divided by the total mass, you find the center of the mass for the x position is 0.5 meters. Okay, does that make sense? Where would you try to find the mass middle of this triangle? If you were given such a triangle, where would you want to find, where would you balance it? You might, okay, well, I got a 1 kilo here, a 1 kilo here, and a 3 exactly in the middle. So in terms of the x position horizontally, how I want to balance it, I want to come to the middle. I want to find a 0.5 meter location. That makes sense. But in terms of the y position, where would you balance it? You got a 3 kilo over there, but 1 and 2 kilos at the bottom. The 3 kilos is a little bit heavier, right? So you probably will put your finger a little bit closer to the 3 kilo because that's a little bit heavier. It's average position of the weight, right? So you need to find a place that is closer to the 3 kilos to balance it. And does our math support that intuition? You can plug in your y positions for each of them, okay? The y for first mass is 0, y for second mass is 0. And the y for the third mass, this you need to do a little quick calculation using trig. You can see, well, I need to know this side. So which means the y position of the 3 kilos and is also this length, which is 1 meters times cosine of 30 degrees. And that is 0.86 meters. So you can find, well, in terms of my y position is a little bit higher than my middle point, which makes sense because you got a heavier mass on the other side. Okay, so that's a quick example. How do you calculate center of the mass?
Professor, quick question.
Yeah.
The diagram shows that, is it saying that the y-axis, that each side is a meter, right? Or is it that the y is a meter?
Oh, each side is a meter.
Oh, okay. That makes sense. Thank you.
So, okay, so this side is a meter.
Okay, sorry, I saw it kind of like by the y-axis and I wasn't sure which one it was. Okay, thank you.
Sure, good question. Let's try to do, yeah, go ahead.
Can you reiterate why it's 0.866 meters instead of 1?
Oh, because, let me draw this again, because my diagram is crowded. This is 1 meter, this is 1 meter. And this is my y, right? And this is 60, this is 30. So I want to find y. You can do, okay, cosine of 60 degrees is the y position over 1 meter. So y is cosine 60 times 1 meter. That is 0.866 meters. Oh, sorry, this is the sine 60. You could do cosine of 30, or you can do sine 60. That will give you 0.866 meters. For this vertical height, which is the y position of the 3 kilogram mass, does that make sense?
Okay, I see.
Okay, thank you. Now let's try to do one by ourselves. Okay, so now we have 4 different floor tiles that are uniformly distributed. Okay, so you got this 1, right? 2, 3, and 4. You got 4 of them. They're laid out in this L shape. Can you find the X? I'm only asking about the excuse me, X coordinates of the center of mass of this entire L shape. What would you do? So think about it. If I ask you about one of them, you probably know where it is, right? If I ask you about another one, you all know where it is. But now I'm asking all together, can you find the X coordinates of the center of mass? So let's have a discussion, a couple minutes, and then I will bring you back for discussion together. Make sure you record the question before you leave to the breakout rooms. I will be visiting room 7 today. Hello, Adrian and Grant and Miko. How are you doing today?
I'm doing good.
Good. Glad to hear that. What are your thoughts? Let's have a discussion. What are your thoughts to this question? How do we find the X coordinate of the center of mass?
I was kind of thinking it was going to be the 1/4 meters because we have one, so we have like one object that is moved 1 meter over, and so that's going to give it a value of 1 at the top, and then all the 3 other objects are going to have a 0 value for that X.
Okay.
So you're going to get a 1 on top for the numerator of the, I don't know, series function.
I see. So you're trying to, okay, so let's just write out what you said. So this one is at a 0, 0. This one is at 1, 0. This, oh, sorry. 0, 0. This is at 0, 1, 0, 2. And only this one is a 1, right?
Yeah.
Okay, very good. I'm sorry, and then continue. What were you gonna say?
And then we know that the objects have a mass of, I don't know, like 4, because assuming every object has a mass of the same mass, or the tiles. So then the numerator is going to be 4.
Yes, all right. So in direct application of the mass of one of the tiles, which is M, at 0, another mass at 0. All these 3 masses are at location of 0. Only the fourth is at 1, and then you have 4 of these tiles added together. So that's 1m over 4m, right? Yes. Very good. That's exactly how we solved this question. Very good. Good job. So this is an example of when you have a combination of a continuous distribution and a discrete distribution. Our approach is to treat each of the tile as a continuous distribution and find the center of mass for each of them. And then you got a 4 discrete distribution. You got 4 points, and then we can use our formula. Excellent job. I will see you shortly after we go back to the main session. Thank you. All right. So you have all come back. Please put in your thought for what you think the x coordinate is, and we'll run the clock for 10 more seconds. All right, I'm gonna go ahead and close the vote. Here is our results. All right. So how did you all deal with this complicated shape?
What I did is I kind of just got all the x coordinates. So because we were only finding the x coordinate for like the 3 kind of vertical ones,
Okay.
their x coordinate for the center of mass ended up being 0 for all 3 of them.
Okay.
And then, so based on the diagram, I think it's saying there's 1 meter between the center of masses of the bottom ones, right? So then that means the x1 would have a center of mass of 1 meter. 1,0 overall would be the center of mass.
Okay.
So then I did, so let me see. Then I did for m total, it's just, well, actually it doesn't even matter in this case, I'm pretty sure. Because as long as they're all, the same, it'll end up being fine. So then we got total mass, let's just use like 4m.
Okay.
And then we got 0 we got m times 0 3 times for the ones on the left. And then the one on the right, we got 1 times m. So we get 1m over 4m equals 1 over 4.
Yes, excellent. Thank you so much, Juan. We first make this continuous distribution into a point. We find the center mass for each of them, and then we can treat them as a discrete distribution. So this is sort of an example of what I said previously. When you have something more complicated, what do? You find the center mass for each of them, and then you find the overall center of the mass for that complicated shape. And you can see that the answer would be 1 over 4 meters. Very good. Excellent.
Professor?
Yeah.
I have a question. Can this also be done just visually? So if I take the top block and put it on top of the block with 1, 0, that would mean that the center of mass is 0.5.
Okay, so you take this and where did you put it?
On top of the single block. And so that would mean that the center of mass is 0.5.
Oh, put it here, the missing?
Mm-hmm.
Okay, then you make a full square, right?
And then, yeah, and that would mean that my center of mass is 0.5.
Mm-hmm.
And so if I put it back to its original position, can I just use that as a guideline of the fulcrum shifting to the left by another half?
Okay, so if it were originally like this, I agree with you, center mass exactly at 0.5. And now you put it here, then I can argue qualitatively the center of the mass should be shifted to the left and also upward. All I can say is has been shifted left and up because more mass is moved left and up. But exactly, is it going to be exactly halfway where you were? And then what about the y direction? Would it be another halfway up in the y direction? I'm not sure if that qualitatively you can get that answer, but it's a very good thought. It's a very, very good qualitative reason.
Okay, thank you.
Excellent. I'm glad that you were all thinking about these different ways to solve this question. So that's an example of how we treat a few different collections of masses. But what if we have a uniform distribution, a uniform rod? Imagine this is my pen. Okay, I want to find the center mass of this pen. You might wonder, well, that's just halfway in between, right? Why bother? Okay. But I want to show that we can actually find this. We can actually solve this. So we're using this, again, this is a definition. If you know the meaning of the definition, you never have to memorize an equation. This is, again, you have very small piece of masses, right? A lot of DMs, and each of them has a position. You add them up, and you divide by the total mass to find the average. So this is the meaning of this equation. And we're going to use this equation to find the center of the mass for this pen. Okay. All right, so the first step would be, well, we wanted to find the center of the mass for the X position because Y doesn't matter, it's one dimensional. I have just 1 over m X dm, okay? So each of them has a X position. This is an X position. X is a variable that changed from 0 to L. The one thing we need to express is this dm. Because X is our variable, we need to integrate over dx. So how do we relate dm to dx? So one way you can do this is simply doing proportion. Thinking about, okay, for an entire pen that a total length of L with a total mass of M, but now I'm only taking a little section of it, which is a total, so this is at a position of X, right? But if you look at the length of that is dx, the infinitesimal small length. So that's dx. And how much does that, how much mass is that dx? So dx over dm is proportional to L over m. So you can get dm is m over L times dx. Okay, so that is quickly, you can do a proportion, you get the answer. Or you can define something called m over L as your line density or linear density of your pen, right? So if you have, what is the density? Density is mass over volume for any object. But right now your object is only one dimension. So instead of dividing by volume, you divide it by length. Okay, so it's just a linear density. So that density times dx, the length, give you the mass. So that is just the one tricky part in this entire calculation. Well, once you have your dm, calculation for the rest of it is very straightforward. I plug in my m over L. M over L is a constant, really. I can take it out of the integral if I want. And then I have x dx, x dx. So let me take the m over L outside of my integration. And what I integrate over is really just x dx from 0 to L. Okay, and what does this become? This becomes 1/2 x squared evaluated from 0 to L, give me 1/2 L squared. So you have 1 over L times 1/2 L squared, give you 1/2 of L. 1/2 of L is right here. Tells me the position of my center of the mass is exactly half of the length in the middle, right? So that's an example of how to do such a problem. We used this equation, okay? Any questions about that particular calculation right there? Any questions? So let's do this question. Here I want a prediction, and then I will show you guys a demo to demonstrate it. Let's say you have a very complicated project, an object, 2 different masses, a hammer and another hammer, for example. They're connected by a string, and then you throw it up. It's flipping, flopping in the air. If I'm asking about the center of the mass of the system, is it still follows a nice parabolic arc, or would you think it's all very messy? So don't have to discuss here. I'm just asking for, what's your intuition? What's your prediction? All right, 10 more seconds, and then we will take a look at the demo, okay? All right, any last minute vote? I'm going to go ahead and close it. All right, so the majority still predicts that the center mass, yes, still follow a parabolic arc. Okay, let's take a look. How can we observe this? So let me switch to a different screen share. Let's take a look at this particular experiment. Okay, so the second time they toss it, it was the exact same object, but now you're not focusing on the spinning, flipping, flopping. You're just focusing on the highlight, the center of the mass, and realize that actually that still follows a parabolic motion. So we wanted to point out that the center of the mass of the object is still described by Newton's second law. Even when the other parts of the object might be really complicated, you can still treat the center of the mass as a point particle, as a point, and apply Newton's second law to it. So if you have a 1 point, what would you do when you toss it? It's going to follow this parabolic trajectory. We have talked about this in 2D motion, and then it still applies to the center of the mass of the object. Now, if the external force is 0, then the acceleration of the center of mass is also 0. This is very important because a lot of times an object is complicated. The other parts of the object, different parts could move different, could have a different acceleration or different velocity. But the center of the mass should have a 0 velocity as long as your total net force is still 0. So we can use that to answer this bridge question. For example, right now we have 2 objects, and one of them have mass m, the other has 2m. They're initially at rest, and there are 2 forces acting on them. One is F this way, one is 2F that way. You're asking about the acceleration of the center of the mass of the entire system. Now, if you view m and 2m together as one system, now what would you do? Well, Newton's second law still applies because its entire system has one total force F acting on it, and that is F to the right. That is your F net, right? And now the total mass is 3m. So the center of the mass will be F over 3m to the right. So that would be, to the left, to the left. That will be the correct answer. So it's really just a correct application of Newton's second law. Now you might wonder, well, okay, I still don't see a big deal about this. There is a much more interesting question and also much more applicable. So let's say now your system consists of 2 people, human beings. They are all the same weight, so they have the same mass, okay? They're standing on ice. They're holding a pole, and the pole is very light. We consider that massless. And they pull on the pole toward each other. And eventually when they meet, where is their location? So when they pull toward each other, do you think they will meet here? Or do they meet here? Or do they meet here? So this is another an actual application we can use what we just learned. So here your system obviously is this entire 2 people, and the pole will be your system. But since the pole is massless, the mass you have to consider is just the 2 human beings, okay? So before they pull, I'm gonna say, before they were just pulling toward each other, they were just standing there now. What is, where is the center of mass of the system? Can you calculate it? Can you tell me, take a look at this system. You have 2 people with the pool. What is the center of the mass of that system?
It's at 0 meters in the x direction, and in the y direction, they appear to be the same height. So I guess it's like wherever their center of mass is.
Yeah, wherever, like maybe around the belly button. Usually that's where our human center of mass is. Yeah, somewhere like there. But if I'm talking about, I'm sorry, this is X position. And I'm talking about the X position is really just in the middle. They're the same weight, so right in the middle. Very good. Now, when they become one, when they stand together, where do you think the center of the mass would be? So when they become one, well, then they all go to the center of the mass, right? These 2 objects become one. So that entire 2 people together is exactly standing at the center of the mass. So during the process of pulling, let's say this is where the center of mass is. Do you think when they are pulling toward each other, this center of the mass will move or not move? Do you think it moves? To figure out whether center of the mass moves or not, we need to look at Newton's second law. So Jacob said, no. And that's correct, because is there any external force acting on the two people? Well, they're pulling toward each other, but that's an internal force. Now, if you look at any outside of forces, well, gravity and normal force balance out, and they're on ice, which means there's no friction. So there is no external force acting on the system, which means the center of the mass has an acceleration of 0. If we're originally there and there's 0 acceleration, and it should not move, right? It should not have changed its original position or velocity, which was at rest at first. So if the center of the mass doesn't move, which means when they meet, the center of mass is still here. But where do they meet? They meet at the center of the mass, because that's now where all the objects are together. So when they meet, they should meet exactly at 0 meters because of the center of the mass of the system hasn't moved. Okay, so that's how we could answer this question. The answer would be 0 meters. Okay, a modified version of this question is you change them to different masses. Now, where would they meet? You can do this on your own, and we will quickly mention this at the beginning of our next class. All right, I'll see you all on Friday, and have a good rest of the week, everyone. Bye-bye.
Thank you, Professor. Bye, see you later.
Bye-bye.
Professor, just real quick, can you go back to the slide that had the integrals?
Oh, yes, I could.
I kind of got lost with the transition from m over L dx to the final piece.
So this is where I was working on it. So from where to where?
From the linear density, and then you went down to...
Oh, to here?
Yeah.
Oh, I just plug in dm into my definition.
Oh, okay.
Yeah, I just plugged this in.
I see. All right, thank you.
Sure. Okay, thank you everyone, bye-bye.